Well, welcome to another video lesson. This one in particular, I'm going to try to squeeze in several things. Mainly it's how to draw ray diagrams for converging lenses. This is what you see on the screen here. I'm also going to show, just because you've seen it before, I can do it fairly quickly. I'm going to show the math associated with converging lenses. And then I'm going to show you how we do a diverging lens problem. Same thing, the math and the diagrams. I'm going to be using pages S34, 35, and 36, as well as the reference page 27. You should recognize this one because it's the same reference page we used for the mirror problems that we did. So I'm going to move along fairly quickly. Of course, you can pause at any time. If I'm drawing things and writing things and you're trying to catch up, just hit pause, but I don't want to make it any longer than I need to. And also, you've seen a lot of this before because we did diagrams with mirrors that were very similar. So we're just going to see a set of rules for drawing rays that go through a lens rather than bouncing off of a mirror. And you've got to be familiar with the types of lenses. These I call double convex lenses because they come out at you in the middle. They're also referred to as converging lenses. And then the next set that we'll do, this type here, is known as a diverging lens, or it can be called a double concave lens. So the idea here is we're going to put something in front of the lens. I always draw my diagrams with an object on the left side. That's what you see here. And we've got to start with the idea that somebody is looking through the lens. So the eyeball is going to be over here somewhere, off to the right. And we want to find out what that person is going to be seeing. Now, what's different about the lens compared to the mirror is that the lens, you're not going to be able to see the actual object. You're only going to see the image when you look through it. With mirrors, the eye was always looking at the real object, and it was also seeing an image at the same time. Just a little difference there. So I'm going to go to page 27 to see a summary of how we draw the light rays. And these are all described in the tutorial. Right below where we have the rules for mirrors, we have the rules for lenses, and you'll see a lot of similarities. Because I'm doing a convex lens, I'm going to leave out the part in parentheses. And the first one says that incident rays that are parallel to the principal axis refract through the focal point. And so here's how we draw that. I'll draw this one in red. We'll always start with an object that looks like an arrow. It just is very easy to draw for you. And we're going to draw one of the billions and billions of light rays that could possibly come off of that thing. One of them just might happen to go parallel to the principal axis. And if it hits the lens, which this one will, there'll be a small refraction, in this case towards the normal because we're going from air into glass. And then another refraction as it comes out of the glass and back into air. That one will be away from the normal. But the net effect is to bend it downward, and in this case, right through the focal point. These double convex lenses have focal points on both sides because you can put an object on either side of the lens, but because we have our object over here on the left, I'm going to refer to the focal point over here on the right as the actual focal point. So for simplicity, we always draw the ray as though it bends just one time rather than once on the way in and once on the way out. We have this line, this imaginary line that cuts the lens right in half. We refer to that as the principal plane. It's easy to get mixed up between principal plane and principal axis. And we draw the ray as though it bends right there, and then it goes down through that focal point. So there is the first rule as I've described it on page 27. The second rule, actually kind of the opposite of that, refers to what I call the other focal point. I even underlined it on page 27. And this, for this particular instance, this is what we'll call the other focal point. It's the one that's on the same side as the object is. So you can imagine an incident ray might just happen to go through that other focal point on the way to the lens. And then it will bend also towards the normal, and then on the way out it'll bend away from the normal. But the net effect is though it all bent one time in the middle, and it comes out parallel to the principal axis. And so it looks like that. So that's how we apply rule number 2. And rule number 3 is the one I'm going to suggest you draw in every instance just because it's so easy. It turns out that a ray that comes off of this object, if it happens to be going right towards the middle of the lens, what ends up happening here is it'll bend just a little bit on the way in and then a little bit on the way out the other direction. And it turns out that if the lens is thin enough, there's almost no refraction at all. So we can draw just a straight line on through there, and it almost shows no refraction. Only the ones that go through the middle end up doing that. So now, remember, our eye is over here somewhere on the right. Lots of different eyes could be looking at this. And the eye is saying, okay, where do all of these refracted rays seem to be diverging from? And that's where it calls the location of the image. And right here is that point. So the arrowhead has its image right here. The rest of the arrow is between the principal axis and there. So I never usually draw that, but we would draw the tail of the arrow right on the principal axis. So there is a tiny little image. And if it's small enough, I might write it like that. And that's what it looks like. So using that forward part description, we would say that this is first inverted. You can see that it's pointed upside down, which also makes it real. Now, one way to see that this is real is just like we did for mirrors. If these rays, after going through the lens, really do intersect, then it's real. And we'll be able to see this on a piece of paper. The eye doesn't tell the difference between real and virtual, but we would know the difference on a piece of paper. And it's also shorter, and it is located between the focal point and what we call the 2F location. The 2F is just twice as far from the lens as the focal point is. So that's how we draw a diagram, in this case for an object that is fairly far from the lens. And let me show you now what the math looks like. The beauty of the math is that it's identical math to what we did for the mirrors. And as long as you get the measurements correct and you get the correct what we call the sign conventions, that's your positives and negatives, then this works fantastic. The sign conventions are also written on page 27. Let me show you here. For our double convex lens, we use a positive focal length. And so if you just count squares, the focal point is 5 units away from the lens. So we'll say the inverse of 5. And then we measure how far the object is from the lens. If we count, that's 15 squares. You can trust me on that, or you can count for yourself. And then a lot of people forget to do this last little inversion step. So if you did that on mirrors, don't make that same mistake here. This will give you 7.5 for DI. Now, a positive image distance always means it's a real image. This is where all the real refracted rays are, over here on the other side. For mirrors, all the real stuff was on the same side as the object, but for lenses, all the real stuff is on the other side because light goes through a lens, doesn't bounce off of it. And then our height calculation, again, I use the form that I wrote on page 27 because it's just already in a nice form for me to use. Take the object's height, multiply it by the magnification, which is DI over DO. There's a negative sign included in that I always put out in the front. So our height of our object is 3 units. DI we just found was 7.5, and DO we had measured before is 15. Okay, so in this case, if you look at these numbers here, 7.5 over 15 is 1/2. So we would call the magnification of this -1/2. Remember, the negative out here in the front really is part of the magnification. And then if we multiply it by 3, it tells us how much our image height is, and that's going to be a -1.5. Now, I always like to compare our numbers from the math with the numbers from the diagram. And you notice our DI of 7.5 falls very nicely in with what we saw here on the diagram. And our image height of -1.5 is also very close. So there's a look at both the diagrams and the math for the convex lens. Let me show you a little twist on this. I'm going to turn the page over, and if you're ready, I'll encourage you to turn it over too. And I'm going to show you what happens on number 3 on page 35. Now, I'm not going to do anything different with the rules, so I'll just draw along here, and again, you can stop this as needed to catch up with me, because I do this a lot. I go a little faster. So here's the ray that starts out parallel to the axis, and will refract right through the focal point. So it looks like that. So that ray is going to strike somebody's eye. Rule number 2 is a little challenging because it says if it goes through the other focal point, which is right here, pointing to it, if it goes through that focal point on the way to the lens, then it would refract parallel to the principal axis. But as you can see, if it goes through this focal point, it's kind of going the wrong direction. So it can't really go down there on the way to the lens. But if you put your straight edge down here, there is a ray that could come off of this arrowhead that would come from that direction and go up towards the lens. It's not obvious, but it does come from a direction where this other focal point is located. This is the one that will refract parallel to the principal axis. Again, I'm drawing all of my refractions as though they happen here at this dashed line. I missed that one just a little bit, but I'm close. And then rule number 3, again, I claim the easiest one is the one that goes right through the center of the lens because it is refracted so minorly that you can just draw it as though it's not refracted at all. So here are a couple more eyes. Green-eyed person, a red-eyed person, black-eyed person going to see these rays. They all see the image in the same location if you can follow these rays backwards. So this is where we need to draw virtual extensions. Now for a lens, anything that goes back onto the side of the lens where the object is, in this case the left, that's all virtual stuff. Because all the real refracted stuff is over here where the eyeballs are located. So we extend all 3 of these. And once you do this enough, you learn that you extend them as you go. You don't do it after the fact, but that's okay. It's worth doing this way the first time. So here is that point where they all seem to diverge. And because it's virtual back there, again, the incident rays are real, but the refracted rays are virtual. We draw a virtual arrow. I might write here that we have our image. In this one, you can see, using the lost method, we would describe as located between the other focal point and the lens. It is certainly taller than the real object is. It is virtual, and it is upright. I'm not going to do the math for this because it really is done the same way. In fact, I use the same lens here. So focal length would be 5, object distance would be 2. And then you could see where the math would get you from there. But I'm going to let you do that on your own because I want to show you one last thing and I don't want this to drag on too long. On page 36, I'm going to show you how these rays refract a little differently in a diverging lens. The diverging lens has the property in that rays that hit it tend to spread out or diverge when they go to the other side. So what I'm going to do, take page 27 here. I'm going to alter the rules that we have here for lenses by adding those words in parentheses. So for example, number 1 says, incident rays parallel to the principal axis refract as though they come through the focal point. Well, if they come that way, we'll draw it parallel to the principal axis. And now here's what you need to know about diverging lenses, and this is a little weird, but they do not have a real focal point. Because the rays never do converge anywhere or focus anywhere, we can't call this, the focal point over here on the right is not the focal point. It has instead a virtual focal point from where everything seems to diverge, and that's over here on the left side. So you got to really change your thinking when you're looking at a diverging lens. So the ray comes out of this lens as though it comes from this virtual focal point. So I'm going to put my straight edge down right where this ray is going to begin here at the principal plane. I'm going to send it up and away, up and to the right. And just to save a little time, I am going to draw its virtual extension because this is what my eye will do. I will follow it straight back to see where that ray seems to come from. So if this is the virtual focal point, then the one over here on the right becomes the other focal point. So rule number 2 says incident rays that would go through the other focal point, and I hope you see why they won't. They can never make it there. So you put your straight edge down as though this ray is going to go directly at that other focal point, but you have to stop at the lens because that's the point where the light ray will bend. And it bends and comes out parallel to the principal axis. This might be one you need to replay again and listen to how I describe that, because it's not the most obvious thing in the world when you look at it. It's hard to tell when somebody sees this green ray here that it was necessarily heading towards that focal point there on the right. The beauty of the third rule is that it looks exactly the same for both lenses. Because we go through the skinny part of the lens, almost nothing refracts there to any great degree, and so we can draw it straight through. So here are the three eyeballs that might be seeing these rays, and everybody has to be able to see the same image. They follow these rays back, and I already extended the red one, so I'm just going to extend the green one now. And we're finding a point where all of these rays seem to diverge from. The black one already has its extension because it is its own extension. So right there where I'm pointing is the location of this image. Notice it's on the wrong side of the lens from where all the real light is, so we have to draw it as a virtual image as best you can. And it's so tiny there, I usually write a little message for somebody so they know where to find the image. So we could describe this one as upright and smaller, located on the virtual side of the lens, between the focal point and the lens itself. And then we could do the math. Now I'll just remind you, looking at the sign conventions, the math is exactly the same. The only thing you have to remember is the focal length for a concave lens is considered negative for it to work in the equation. But nothing else is different about that. Again, I'm not going to show the math on this one just because it's so similar to the mirror problems and the other lens problems. But if your number doesn't give close agreement with this, it looks like this is just about 4, somewhere between 3 and 4. And that'll give you a negative DI because it's a virtual image. So if you don't come out with something close to that, then you ought to maybe stop in and check with me. But always make sure you do, on the ones where I'm not showing it, make sure you do the math. I got a little space down here. And you'll see on pages 34 through 37, there's several other different kinds of lens problems. And the more practice you do, the better you get at it. So I'm going to stop it here, and hopefully this is helpful. If you need more help directly from me, you see me in the classroom. You could certainly replay parts of the video if that's helpful for you. Reading the tutorial and looking at his sample questions could be helpful as well.